Hi everyone. In this lecture, I will make an introduction to Kafka. As you remember, you will use Kafka as the event store in our architecture. It will hold the tweets in the form of events, and you will use multiple event-driven services to subscribe and consume those events. So let's go into the advantages and the architecture of Kafka. Kafka is an open source stream processing platform. It is designed to handle data feeds with low latency and high throughput. It holds the data in an immutable, append-only structure called topics. You can actually call this data as logs or events. Its immutability ensures that you will have all history of data feeds and can get a picture of the data at any point of time. Kafka is fast, resilient, scalable, and works with high throughput. It is resilient as it relies on file system instead of memory, and it keeps all messages on disk. And by doing that, it also keeps a configurable amount of replicas to prevent data loss in case of a failure. It is fast because it relies on disk caching and memory-mapped files of the underlying operating system, instead of garbage collector eligible JVM memory. A memory-mapped file contains the contents of a file in virtual memory. The mapping between a file and memory space enables an application to modify the file by reading and writing directly to the memory. Accessing memory-mapped files is faster than using direct read and write operations, as it operates on memory. In addition to that, in most operating systems, the memory region assigned to a mapped file actually is in kernel's page cache. That means no copies will be created in the user memory space, and it will directly operate on disk cache, which will be faster. So although Kafka uses disk to store the data for resiliency, it actually provides a strong caching mechanism by the disk caching, which actually means it works directly on memory of the underlying operating system most of the time. Kafka has a natural scaling capability thanks to the partitions inside each topic, which again configurable so that you can scale by just increasing the partition number. If ordering is important for you, be sure that you put all related data, which requires ordering, inside the same partition, because ordering only guaranteed in a single partition. And you can achieve to put the related data to the same partition using a partitioning strategy, which you will see in the producer section in the next slides. And finally, the important part for us to use Kafka in our microservices architecture. It is a great match to use in an event-driven microservices environment, as Kafka is a solid platform that can hold events and provides nice producer and consumer APIs to work on events. Here is the basic Kafka architecture, where on the left side you see the Kafka cluster with 3 broker nodes. For high availability, it is better to hold those brokers on different servers. In the middle, we see the data structure of Kafka architecture, where we have 3 topics as an example, and each topic has 3 partitions. So a topic actually consists of 1 or more partitions, which hold the real data or events of your system. We need to feed the data into these topics and partitions, and for that, we have the Kafka producers. Here again, as an example, you see 3 producers. Note that a Kafka producer can tackle multiple threads at the same time nicely. So in most cases, using a single producer might be enough for your system. Now it comes to resiliency. Kafka provides the replicas where you can define a replication factor to replicate the data in each partition on different brokers. And assuming all brokers has their own machines, you are safe that you don't lose any data in case of a failure in a broker. This replication factor can be as much as the broker number to get higher resiliency, but of course with a small performance cost, as with multiple replications, it will require approvals from all of the replicas to finalize the data to be produced on a Kafka topic. This is the default behavior actually, but you can change it as we will see in the producer section in the coming slides. And finally, on the bottom, you see the consumers. Here again we have 3 consumers. This number 3 is important when it comes to the consumers, because it is strongly coupled with the partitions on a topic, such that each partition can only be assigned to a single consumer. For example, in this system, considering topic 1, partition 1 could be assigned to consumer 1, then partition 2 to consumer 2, and partition 3 to consumer 3. It is not possible to read a single partition by multiple consumers. On the other hand, it is possible to read multiple partitions from a single consumer. In this case, if I add a 4th partition, I can simply add a new consumer to be assigned to that partition, although I could also use one of the previous consumers and assign it to the newly created partition. And exactly at this point, we come to the scalability property of Kafka. Yes, I can use a single consumer to consume all the partitions. But what happens when I have 100 partitions and want to consume each partition in parallel concurrently? In that case, I can simply add more consumers up to the number of partition number, in this case say 100 consumers, and then can use different threads or even use different processes to consume each partition. This way, Kafka naturally scales and provides high throughput with low latency, as you can distribute the work among the consumers on different levels. You can use threads in a single process, or processes on a single machine, or even processes on different physical machines. It is totally up to you to configure this concurrency level. Now that we have a general understanding about Kafka architecture, let's go over some important Kafka producer properties that we will be using during Kafka producer implementation. This will help us to understand how a Kafka producer works under the hood. First of all, a Kafka producer holds a buffer of unsent records per partition and send the records to the cluster using an internal batch size property. In most of the cases, the default batch size value would be good enough, but you may want to play around with this value to get a better throughput by increasing the batching in your system. The smaller the batch size, the less throughput, and if batch size is too big, the memory will be wasted, since the part of the memory that is allocated for batching will not be used. This is because the data will be sent before the batch size limit hits. Using a larger batch size makes compression more efficient, and if a data is larger than the batch size, it will not be batched. In the next slides, I will explain compression type a bit more in detail. Under heavy load, batching will probably be in place. However, in a light load, data may not be batched until the batch size limit hits, because there is also a timeout that producer can wait before sending the data. In this case, there is still an option to help us increase the batching on the producer side. We can use linear MS property for this. Default value for this property is 0, and setting it to a higher value will cause the producer to wait for a defined value in milliseconds. So setting it to 10 will cause a 10 millisecond delay for each send on the producer. Note that, yes, this will increase the throughput, but it will also cause a delay as the producer will wait more before sending the data. Again, this is a property to be tuned carefully by taking a good attention by looking at the system facts as well as the data itself. The buffers are sent as fast as brokers can keep up, and this can be limited using max in-flight request per connection property. If you set this property to 1, any subsequent send requests will wait the previous one to return the result. As mentioned previously, in Kafka, there are multiple broker nodes that hold the same data to enable resiliency. By default, producer will wait all replica nodes to return a result, because the default value for acknowledge property is all. By setting acknowledge to 1, only the broker that gets the request will send confirmation instead of waiting all in-sync replicas. And if you set acknowledge to 0, you can skip confirmation. But be careful, in that case, you will lose resiliency totally. So there is another trade-off here between the performance and resiliency, as you can see. The producer property compression type allows to set compression on producer level. Default value is none. That means there will be no compression. This setting can be set to none, gzip, snappy, or lz4. The compression is done by batch and can be improved with larger batch sizes. So by using compressed data, you can send more data at once through the network and increase the throughput. End-to-end compression is also possible if the Kafka broker config compression type set to producer. Then the compressed data will be sent from a producer, then will go to the topic and return to any consumer in the compressed format. This way, compression only happens once and is reused by the broker and the consumer. The producer config property request timeout milliseconds defaults to 30 seconds. It is a client property, and it causes the client to wait that much time for the server to respond to a request. The producer config property retries causes to retry a request if producer doesn't get an acknowledgement from Kafka broker. This property defaults to 0. It is not that if you set retry value greater than 0, there will be a possibility that the order of messages will be lost, because any failed data can be inserted in the second try, and it will be inserted after the records that naturally comes after it. To prevent this, you can use max in-flight request per connection property and set it to 1, so that you can only send one record at a time. But of course, this will affect the performance, because you cannot use batching in that case. So you need to decide if ordering is important for you. Again, here is another trade-off that you need to decide between ordering and performance. The producer config property partitioner class sets the partition strategy. By default, partitioner class is set to default partitioner. Default partitioner uses a round-robin approach to distribute the load on partitions. That means it will send the data to available partitions one by one in rational order. Finally, here is a summary of the properties that we will explicitly set in our producer implementation section. I will take your attention on the configurations and remind the description of each when we are using them. Alright, let's continue with adding the config data module in the next lecture.